Hello, everyone. My name is Shengxuan Liu from ByteDance, and today I will make this sharing with Dr. Beinan Wang from Alluxio. So in this session, I will mainly focus on how Alluxio Local Cache accelerate the Presto in ByteDance. And after that, Beinan will cover the Alluxio's most updated cache technology and performance. So let's get started. I will firstly describe our integration of Presto and Alluxio Local Cache, and so in details we will cover firstly how we use the Presto, and then I will talk about how we integrate these two components, the Alluxio Local Cache and the Presto, and then I will talk about how we use the cache efficiently. And then we will talk about the performance gains and future plans. So for the Presto usages, we have about 2 million read-only interactive SQLs every day. And we deploy our Presto cluster in the Kubernetes. And these are the size of these instances. We have 96 cores and 384 gigabytes of memory and 550 gigabytes of SSD. And the SSD is used to store the cache. And for the data source, we are using Presto to query the Hive tables that are stored on the HDFS. And for the metadata service, we're using the Hive Metastore or HMS for the metadata service. And also we're using some other engines like Spark. So why caching? So every time we're talking about cache, the very first question is why we need the cache. So why? And here's the reasons. We have done a lot of performance analysis, and we found that I/O is always the most time-consuming in the SQL execution, right? And also, reading from HDFS is not stable, and massive reading in the slow data node always slows down. Always slow down the performance of the Presto, and many CPU time are wasted. And the third reason is that Presto is a distributed cluster, and its computation also needs some network bandwidth. For example, shuffling, it needs the network transmissions among other workers. So we can save the network bandwidth for other operations. So these are the reasons why we need a cache. So now I will talk about how we integrate the Alluxio Local Cache to our Presto, and I will mainly divide it into 3 components. The first is the data consistency. The data consistency means that how we make sure that we're reading the correct data and we're not reading the dirty data. Secondly, the data locality. So the data locality means the frameworks of the framework of the storage of the distributed cache. And we have 2 main strategies: the soft affinity and consistent hashing. Third is the data orchestration. It means that how we use the cache efficiently. And for this one, we introduce our own cache strategies. So let's talk about the first integration challenge, data consistency. So we found that the standard Alluxio Local Cache is not enough for our usages because some HDFS files might be mutable. It means that the file might be updated later. But however, the local cache cannot be updated at the same time. So it means that the HDFS files can be changed, but the cache files are not changed. So, and this problem introduced the inconsistent issue of between the HDFS files and the local cache files. So to resolve this data consistent issue, we introduced Alluxio paid versioning strategy. So we use the last modification time from HDFS metadata to determine if the cache is up to date. So And in the naming of this cached files, we add one more element into the cache storage path. As you can see in this example, the storage path is very meaningful because it contains a lot of Alluxio Local Cache metadata. You see, and in our usages, we added the end time. It means the last modification time as the cache file name. So in this case, we are able to store the last modification time with the local cache, with the local cached page files. So, and this is how we store this last modification time into this into the cache metadata. And obviously we are able to store this last modification time, but now we need to use it to verify if the cache is valid. And here's the steps. When reading data, we get the last modification time from the corresponding HDFS files. And at this point, we only read the HDFS metadata. We are not downloading the entire file, right? And then we compare this last modification time to the local pages last modification time. And obviously, if there's a match, we read from local page. Otherwise, we use the HDFS files and we download it to the local, and then we also need to update the last modification time in the local cache storage path. So this is the first part of this these three steps of the Alluxio cache integration, and this is how we make sure that the data is consistent from the between the local cache and HDFS. So now I would like to talk about the data locality. So the data locality means that how we store the local stored cache in this distributed cluster. So before using cache, the coordinator sends the splits to random workers. But after using the local cache, each worker only stores a small portion of the entire cache data. So because we cannot have a copy of the entire cache in each worker, right? So the first challenge is that how to assign the split to the workers that store the cache locally, right? So otherwise we cannot take advantage of this existing cache because the worker does not have the cache locally, right? So to resolve this problem, we are using the soft affinity scheduling strategies. The soft affinity scheduling is to try to assign the same split to the same worker. So at every time, the worker stores the cache at the very beginning. The worker stores the cache locally, and then when the same split comes to the worker, it can be loaded from the local cache instead of the HDFS, so it can improve the performance. And so how do we determine that? So we're using the hash code of the split metadata to determine the preferred worker, right? So because the hash code of the same input, and here I mean the split metadata, it doesn't change every time. Right? So each split can be assigned to to only one preferred worker, and the preferred worker means that the worker is able to cache the split data. So on the other hand, if there are some situations that we fail to assign the split to the preferred worker. For example, the preferred worker is very busy, so the coordinator chooses the least busy worker for the split. So in this case, this worker cannot store this cache. So, and this is about the soft affinity scheduling. So now I would like to talk about another strategy, consistent hashing. So so as I just described, the soft affinity uses hashing of the split metadata to determine the target worker for the local cache storage. But the second challenge is that what if we need to add or remove workers? For example, if we have 5 workers, we can use a modulus to determine assignment of the incoming split. For example, number 0 and 5 and 10, these numbers go to the first worker, and number 1, 6, 11 go to the second worker, right? But what if we have 4 workers? Number 5 needs to go to a worker, the second worker instead of the first one, right? And the same problem will also be there when we have 6 workers. So if we add or remove some workers, the assignment changes, right? So in this case, we need to do the rehashing and the relocation of all the splits when we are, adding or removing workers. So, and to resolve this issue, we introduced consistent hashing to find the preferred worker. In short, the consistent hashing assigns a range of the hash values to one worker. So in short, we distribute servers evenly into a hash ring, and then we'll compute the hash code of each split and map them into the hash ring. So as I mentioned, each worker is assigned a range of the hash code. So we find the nearest server on the hash ring clockwise to find the most preferred worker for the incoming split. And if we remove or add some workers, it only affects the worker nearby clockwise. For example, if we remove one worker, its range will be assigned to its nearby worker. And if we add one worker, the nearby worker will be affected only. Its range will be divided into 2 parts and shared by the new worker. So in this case, we can minimize the number of the split relocation when adding or removing workers. So now we are using 2 strategies, the soft affinity and consistent hashing, to resolve this data locality issues. So after that, I would like to talk about the data orchestration. The data orchestration is about how we use the cache data efficiently. After integration of the cache, we found some problems. So the Presto worker caches everything. It caches all the split data. But the problem is that not every split should be cached, because some data are not popular, and the frequency of the usage of this non-popular data is pretty low. So it causes the poor cache hit rate ratio, right? And because we have a lot of data and the cache size is fixed, so the second problem is that there will be a very frequent data eviction. And to resolve these problems, we implemented our cache strategies. The cache strategy is more related to the business logics. So we introduced the cache admission. It means that we only cache the hot data or the popular data. And how to find the or how to determine which data is hot. So we do some analysis on the past week's core pattern, and we can find, we do some analysis based on this pattern, and we can find the potential hot tables, right? And then we use this data to for our cache strategy. And in our cache strategy, we have the database name, the table name, and the partition, and the TTL. Right. So let's say probably one partition is only, we only cache one partition for 2 days. And then for another partition, we keep it for 3 days. Right. So this is how the TTL works. and about the workflow, how we use this cache strategy. The Presto coordinator checks the data against the cache strategy. So if there's a hit, it means that this data should be cached. It's in the strategy. Then we use the caching workflow. And the caching workflow basically is what I just described. So the coordinator assigns the workers according to the soft affinity, and the workers tries to store the non-cache data locally, right? Otherwise, if the data is not in the cache strategy, we use the normal workflow. So basically, it is what the normal Presto does. The coordinator choose some random workers and assign the space as the normal Presto does. Yes, and these are the and this is about the data orchestration and the data cache strategies. I have introduced our integration of the Presto with the Alluxio Local Cache, and here's are the performance results. So firstly, for the TPCDS 1 terabyte data, we observed a 10% improvement for the end-to-end executions. And however, in reality, simple queries are more suitable for the Presto local cache. And in our internal queries, we mainly onboard the simple and reading intensive queries to this caching system. So in this case, we have observed a 50% improvement on the table scan and aggregation queries. These queries are pretty simple, and we also find that there's a basically 1x improvement for the most reading intensive queries. So these are our performance results. And now, thanks to everyone, I would like to pass it to Dr. Beinan Wang, and Dr. Beinan Wang will continue to do this sharing.
Thank you, Shengxuan. Thank you for your contribution and contribute it back to the community. So today I will share some our observation about the other benefits of our local cache. So I think the first benefit I would like to share is the cost saving part, because we are seeing more and more Presto user, they are lift their Presto to cloud, something like the AWS, GCP. But when they are using the Presto on cloud, they might prefer to use the native cloud storage, something like S3 or GCS on the cloud. But the thing is, the cost model of this kind of storage is based on the number of requests, or we can see the number of API calls. We are seeing that there's a lot of data API calls that should be much more than the metadata API calls. So by using our Alluxio SDK cache or local cache, it can save a lot of the data API calls. It's based on your cache hit rate. Also, some of the user, they might fetch data from the other region or maybe the other cloud. So I think most of the cloud provider will charge you some data transfer fees. If you're using S3, they call the egress fees, which means if you are reading the data from the other region, the cost is a little bit high. Because Presto is a super powerful data engine. It will scan maybe terabytes of data from the storage. So we are seeing when we are using something like 100% of the cache capacity of the working set, which means when you read 1 terabyte from the storage, you can just put 10 terabytes as the cache. Then we can mostly save your 50% of cost, just because it also depends on your workload and depends on the cache hit rate. But mostly, I think for the most workload, Presto workload, they are repeatedly to read some hot tables. So in this case, we can save a lot of cost and get a really good cache hit rate. We are also seeing some stability improvement by using the local cache. just because no matter you're using the Presto on-premise or on cloud, we are seeing it's a lot of spec about on the network transfer. The Presto is actually is hitting the name node or the S3 storage too much actually. So by using this cache, we can see it will eliminate the specs, and also it can reduce the risk of the hot data from the hot data node, because if you have some really hot file to scan, which means you might overload some data node if you're using HDFS. But if you're using S3 or DCS, it's probably the same thing. It might be throttle the gateway or whatever. So you can just use the cache. It can somehow to reduce the number of requests to the hot data file, just because the hot file is always in the cache. Am I right? And also it can prevent the overloading or throttling of the under storage, because for most of the storage on cloud, they may set some threshold, they may put some access control there. So if they found the some of the nodes or the entire cluster is too hot, they might reject your request. So which means you may see your query fail or something. So by using the cache, it can significantly reduce the risk of such kind of overloading or throttling. Okay, so then I will share some future works about our local cache or Alluxio cache. The first one will be the Semantic Cache, the next one is the native Parquet reader, and the third one is the distributed cache. Just because by using the cache, a lot of the user reports that they are seeing some read amplification, because the cache will cache the entire file or the entire block, maybe the entire page of the data. But actually, for each Presto read, they may just read a very small piece from based on your data format, something like a Parquet or like Orc. Because the Presto is using something called predicated pushdown, which means they won't read all of the file, so through the very beginning to the very end, right? So they just read a very small piece in the middle. So in this case, if we cache something like 1 megabyte or 64 megabytes, it costs read amplification. You can see the net bandwidth will higher than you expect. So we are trying to do some semantic cache just based on your data format, which means we have probably 0 read amplification, so we can save a lot of the cost on the network and the bandwidth. And also, for sure, it's also some performance gain. The second future work is we are trying to make a native Parquet reader. We want to implement in Rust, which can provide a much safer memory model. And also it will support something like SIMD to improve the performance. And also we plan to support the predicted pushdown in this Parquet reader. And we will try to integrate the new Parquet reader into Presto, maybe also other storage or compute. Just based on our experiments and also the dashboard from the production, we are seeing cache hit rate is highly related with the capacity of the cache. But the thing is, probably your Presto cluster might have very limited SSD resource, which means probably you don't have enough cache space to cache the data, so you won't get the best cache hit rate. In this case, you can try to deploy another cache cluster we call the Alluxio system cache. We are just delivered the next generation of the distributed cache we call Dora. On the right side, we can see the performance gain. It's the Dora. It's the end-to-end latency. We can see by using the Dora, when the cache is warm, we can see at least 10 times performance improvement compared with the older Alluxio distributed cache. And also for our new Dora cache, we provide a high availabilities, because there's no single point failure. We get rid of the masters. And we also provide the client-side fallback. even the entire cluster is down, the Presto can still fall back to the under layer storage directly. You can still read the data. And also, just as I mentioned, because we are using a distributed cache, it won't give you any limitation on your cache capacity. So you can definitely get a cache hit rate. And also we try to optimize the position rate from Presto. If you are using Parquet or Aux, this kind of data, columnar data format, you can see a much better performance. Okay, thank you for joining our session. I think that's everything we want to share today. So if you have any questions, you can feel free to ask in the chat channel. Thank you for joining our session.
Thank you, everyone.